Hello, I'm Billy Younger, and this is the series on vector addition. We're actually getting ready to do vector addition part 2. We did vector addition part 1, which was basically showing you all the ways that you could specify a vector's magnitude and direction, and also gave you a little bit of background information about ways you could choose coordinate systems to make things a little smarter. Then I did the optional portion of vector addition, which was about special angles, special triangles, and stuff of that sort. And now we're getting ready to do vector addition part 2, where I'm going to introduce a problem where we're supposed to add 4 vectors. And I'm going to, in part 1, show you how to decompose the first of those vectors into X and Y components, choosing their sign. And then when it's all said and done, all the different parts will be put together so that you can use the results for each of those to solve the vector problem that's initially stated. So let us start by sharing my screen so you can see the actual problem we're attempting to solve. I'm asking what is the resultant, which is another word for the sum of all the vectors. In this case, it's going to be called R for resultant, and it's the vector R is equal to A plus B plus C plus D. When we write vectors, we usually take their symbol, use a capital letter, and then put a arrow over top of it. When you type them, you usually just use bold print. I did both here. But if the vectors A, B, C, and D are defined as follows below, notice A is 20 newtons at 30 degrees. B is 14.14 newtons at 45 degrees west of north. And then C is 50.00 newtons at 231.34 degrees. And finally, vector D is at 25.00 newtons at a compass heading of 106.26 degrees. So that's the problem. I am going to probably show you this in each of the parts, and each of the parts I'm going to do a separate vector. So this vector we're working on part A, on vector A, and I've already written it down on my notes. Let me stop sharing. And now I'm going to turn on my document cam. So as the sheet said, vector A is supposed to be a 20 Newton vector, and it's pointing at 30 degrees. When we see a vector that just says at 30 degrees, or at 40 degrees or at negative 12 degrees, we know we're in math mode. And math mode is such that whenever they just say an angle, it's measured, if it's positive, counterclockwise from the positive x-axis. If it's negative, it's going to be measured clockwise from the positive x-axis. So I'm going to draw my axes here. This is my x-axis. This is my y-axis. Of course, that also corresponds to east. That also corresponds to north. And as far as compass headings, that's 0 degrees, and this is 90 degrees. But the main thing is I'm doing 30 degrees, which is roughly this angle. That's going to be my vector A. And in fact, I can express its magnitude as A with absolute value bars around it, or I can just write it as A with no vector symbol. And that's equal to 20.00 newtons. And this angle right here is 30 degrees. Of course, we could also have expressed this as 60 degrees east of north, or 30 degrees north of east, or we could have just said it's a compass heading of 60 degrees. There's a lot of different ways we can express that. The main thing is when you have a vector, you want to resolve it up and resolve it into components that are parallel to the x-axis, y-axis, and or z-axis. In this case, we're only doing 2 dimensions, so we only need the components parallel to the x-axis and y-axis, because once we have vectors down to individual components, then it's just a matter of adding positive and negative numbers. Vector components that point in the positive x direction are, of course, positive, and vector components that point in the negative x direction are, of course, negative. Vectors that point in the positive y direction are positive, and vectors that point in the negative direction are negative. And that just means their components are. The vectors themselves, of course, have magnitudes that are positive, but we end up just adding vectors as positive and negative numbers. So what we see with this particular vector is, one, if I wish to find out what the components are, I got to imagine being able to walk from the tail to the head. If you do it along the vector, then unless the vector is lying along one of the axes, you don't know what the x or y components are. But if you choose to leave the tail of the vector and walk to get to the head the quickest way possible, then you have to, and walking along an axis, you either have to walk along the x-axis or the y-axis. In this case, notice I'm actually walking along the x-axis in the positive direction. So that means this is the x component of the vector. And in fact, since it's in the positive direction, we're going to treat its magnitude, or actually we're going to treat its numerical value as positive. Similarly, we then have to hang a left and walk parallel to the y-axis. You could put it right here if you wanted. Then your vectors would be tail to tail. And of course, to add vectors that are tail to tail, you complete the parallelogram and draw from the common tail to the common head. But I'm just going to do it like this, as if it were an actual journey of walking. That too is in the positive direction, and this is going to be called a sub y vector. Okay, I labeled the vectors because they actually had heads. If I just put the magnitude up here, I could call this ay equals positive something and ax equals positive something. So that's my two components. And what I recommend all my students do, at least initially till you get really well experienced with this, is go ahead and write out what the cosine and sine of the given angle is. So I'm going to write, for instance, that the cosine of 30 degrees, according to this diagram, and SOHCAHTOA, so means sine equals opposite over hypotenuse, CA means cosine equals adjacent over hypotenuse, and TOA means tangent equals opposite over adjacent. So cosine is CA, which means adjacent over hypotenuse. So that's AX over A. Sine, on the other hand, is so is sine equals opposite over hypotenuse. The opposite angle, of course, is AY, or excuse me, the opposite side is, of course, AY, and the hypotenuse is, of course, A. So now we can use the algebra to actually solve for a sub x and solve for a sub y. Obviously, we're going to multiply both sides by a, canceling out the a with this a here and getting an a here. And that gives me, of course, a x is equal to the magnitude of a, which is 20.00 newtons, times the cosine of 30 degrees. And if you recall from our special angles, the cosine of 30 degrees is actually √3/2. So I could actually write this as √3/2. Of course, that √3/2, the 2 would cancel out with the 20 and just leave us 10 times the square root of 3. So force that to be positive because I know the x component is positive. I'll stick a positive here. And now I'm going to take basically 10 times the square root of 20. This is a part you don't have to do. You can just add it, multiply it out with your calculator, and that's fine. But if you want to get fast at it, this is the best way to do it. So I'm going to take √3/2. The 2 will cancel out with the 2 and the 20 and leave 10. And then I'll do 10 times the square root of 3, which is 17.32 newtons to the appropriate number of sig figs. AY, similarly, is equal to, again, it's a positive direction, so I'm going to force the sign, and I want you to do that every time, 20.00 newtons, and times the sine of 30. Again, this just comes from taking and multiplying both sides of this equation by a. If I multiply by a, that would cancel that one out, but I get an a here, and that's what I've got there. Now, the sine of 30 is, of course, 1/2. So this guy right here is just 1/2. So 1/2 of 20 is 10. So that's 10.00 newtons. And that's basically the same thing we did this, which was the square root of 3/2 from our special angles. So now we actually have the x and y components. And if we wish to continue with solving this resultant problem, trying to find the sum of a plus b plus c and plus d, all I'm going to do is break a, b, c, and d into its x and y components, into each of their x and y components. I'm going to add all the x components to get the x component of the resultant. I'm going to add all the y components to get the y component of the resultants. And I got to make sure that all those components have the right sign. Then when that's all said and done, I'll have the resultant vector's x component, the resultant vector's y component. I can redraw that in xy coordinate system. I can use Pythagorean theorem to figure out the magnitude, and I can use basic trigonometry. Usually we use the tangent function to find the actual angle that it makes with, say, the nearest axis, and then we can put that in some common notation like the ones I introduced in part 1. So that's it. You should be able to do this on your own. I suggest you pause the video, see if you can come up with all these with your own calculator. Then look back, and I'm going to actually give you 2 problems to try. So here's ones I suggest you should try. And what I want you to do is I want you to perhaps write down what the vector I'm saying is, V1 is going to be 50.00 newtons, and that's going to be at an angle of 38.66 degrees. Pause that, try to find its X and Y component, and then come back to this. I'm going to also now write V2, which I'd like you to try as well. Again, what I recommend is you go through, copy this, then come back and after you've solved it, see if you get the same answer that I do, because I'm going to give you the answers. So V2 is 14.14 newtons, and that's going to be at a compass heading of 45 degrees. So now you can copy down this vector as well, work it out, find what its X and Y components are, and then come back and see what the answers are, because I'm now going to write the answers that I've worked out. If you find I made an error on any of this, please give me a send me an email at billy@physicssolutions.com. That's all one word, billy@physicssolutions.com. So V1X, what I got for that is a positive 30.00 newtons, and V1Y, what I got for that is a positive 40.00 newtons, and V2X, what I got for that was a positive 10.00 newtons, and V2Y, what I got for that was a positive 10.00 newtons. You might think, well, that's weird. Why do we got all positives? Well, that's the nature of quadrant one. Remember, with the Cartesian plane, this first quadrant right here is called quadrant one. This one is quadrant two. This one down here is quadrant three. And this one down here is quadrant four. And you can see that in order for me to go from the origin to any point over here, I need to go in the positive X direction. So that's why the X component is positive. And I need to go in the positive Y direction. And that's why the positive Y component is positive, or excuse me, that's why the Y component is positive. So this is a characteristic of quadrant one vectors, is they always have both positive and both positive components in the X and Y direction. I don't want you to memorize it that way. You really just use that as a check if you want to. The main thing is always try to walk from the tail of the vector to the head of the vector going along coordinate axes. That way you won't make a mistake. Even if you, for instance, had chosen to go first along the Y axis and then along the X axis, you still would have had to go, okay, well, I need to get higher, so I'm going to walk up this way. That must be my Y component. That is clearly in the positive Y direction. And then I hang a right, and that's clearly in the positive X direction, so that's positive as well. So it doesn't matter which way you choose to go. You just need to consider walking from the tail of the vector to the head of the vector along the coordinate axes, and the direction you go tells you what those components are, assuming the vector is lying at the origin with the point pointing out into that quadrant. Well, that's enough for part two of this video. I hope that helps everyone try to perhaps better understand how vectors work and how to break them up into components. That will be the end, and I'll be posting a part 3 in a second. Have a good day.